back and added different examples because the one we used yesterday wasn't the prettiest one. So in our case right now, we're talking about linear regression and we're doing an inference for the slope. So yesterday I added all these different math stuff that again will appeal to those who are interested, but I imagine that there's not that many in this class. So guys, keep the side conversations to a minimum, all right? So yesterday I went over the conditions, and there's a lot of conditions. There's 5 of them. We talked about reading regression outputs and how that's actually very important for these type of problems, especially if you're not given the data, then how else are you supposed to do these problems, all right, other than being given the computer output. I went back and added some sampling distribution proofs that, again, will only appeal to those who are interested, but again, don't imagine there's a lot here. In the slides yesterday, we talked about the confidence interval for the slope and how yesterday I talked about how the standard error is not given to you in the problem or in the calculator. So we do have to find a way to find it, and I'll go over at least one method that's the easiest way to find it. Well, the other method is to use the formula that you see right here, where the standard error of the slope estimate is s over s sub x times the square root of n minus 1. There you can find everything you need to plug in values into this formula to find that the standard error, but there is a slightly easier way to do that, so I'll go over that soon, all right? And yesterday we went over an example. I did not use this example yesterday. I changed it out, and I went back and also added the computer output for these examples, which we didn't have yesterday. So I will do hypothesis tests, but also do the calculations for confidence intervals with that other example, so you guys could see how to use the computer output for that problem. All right, so this section is more about, where to find everything. Not so much, not so hard computationally, but just finding where everything is more of a challenge than not, okay? Before I move on to hypothesis tests, are there any questions about confidence intervals before moving forward? No. All right then. In that case, I'll talk about hypothesis tests. It's not going to take a very long time, but the example will take more time probably than going over the slides. All right, so as with any hypothesis tests that we've had, the hypotheses need to be stated at the beginning. We're doing an inference on beta, which is the estimate of the slope of that population regression line. Just like what we did for differences, like difference in means, difference in proportion, or paired data, we're going to assume that the null hypothesis, that the slope is going to be equal to 0, because as you see at the very bottom, having a slope of 0, going back to unit 2, having a slope of 0 means no association, right? Because the slope gives us the information about the direction of the association, whether it's positive or negatively associated. But if having a slope of 0, whether that number is neither positive nor negative, then we're going to assume at the beginning that there is no association between variables, and then we're going to then try to find evidence for the alternative, that the slope is negative, indicating a negative association, that is positive, that it's a positive association, or that is not equal to 0, which suggests that there is a association there, okay? Or an association, bad English. All right, an association between the variables, all right? That's what we're aiming for right now, okay? Under the null hypothesis, if we assume that beta is equal to 0, and already, again, I talked about this yesterday, we are going to assume that we do not know what this sigma is. Rarely, again, you have to get all the observations from the population, which we don't typically get. So therefore, this sigma is unknown to us. So therefore, the sampling distribution of B has an approximate, or has a normal distribution with a mean of 0. That's our null. And then this variance. But because we don't know what this sigma is, we approximate it with the t distribution with n minus 2 degrees of freedom, not n minus 1. Okay, so that's not a typo. It's supposed to be n minus 2. And then if this is the sampling distribution of B, then we take B, subtract the hypothesized value, which we're assuming to be 0, divide by the standard deviation, which is the square root of this guy, and then with some algebra, you're going to be able to simplify it so that you're dividing by the standard error of B as you're supposed to be doing. All right? All right, so that's our test statistic, and that's our sampling distribution. And once we have our sample statistic, we plug in the necessary values, we get a p-value, we make a decision. Here's the recipe. All right, so very quick hypothesis test. There is a typo right here. It's supposed to be test, not interval. The things that come with copy and paste. All right, so our parameter is beta. We're doing a t-test for the slope. Here are our hypotheses. Again, I've never seen a problem on the AP test that College Board has given students where the slope was not 0. It's always been 0, so we're just going to assume that that's always going to be the case for us. Conditions are the same, and then the test statistic is right there, and then we have our interpretation the same as before. All right, so that's our t-test for the slope of a regression line, and that's your last recipe for this class. Any questions before I move on to an example? Okay, and again, I'm going to be doing a lot of calculator work and referencing to the computer output. So again, make sure you guys are paying attention because it's annoying having to repeat stuff that I said before already. So please make sure that you guys, if you guys are following along, please make sure that you are closely. And again, if you're not paying attention, then I don't know, you might miss something important. All right, so our example right here, we're talking about male subjects between the ages of 25 and 30, and their blood pressure and weight was recorded. So our task right now is at the 1% significance level, is there a relationship between systolic blood pressure and their weight? Okay, so the data is right here, so that's an indication that you should try to start putting these in your list. One thing about this table that I realized in first block is very poorly structured is that you do have to make sure that they're paired, right? So please make sure that as you go left to right in the first row, make sure that these numbers are paired together, and then once you're done with the first row, you have to wrap back around to the second row and input those values. So it is kind of poorly structured, but that's the way I did it so I could fit it all on one slide. So please make sure that when you input the data, that you input the first row there, that matches the first row here.
So it's all
Okay.
one row? Or like one first?
So in your calculator, you're gonna put in the first row right here, and then follow it up with the second row. That's one list,
Okay.
and then the second list is this guy with that guy. Okay, and make sure that they're paired like this. Okay, not like paired like, they're not paired like this. Okay, even though that probably would have been better, but it's okay. All right, so just put those in. You should have 20 for each of them, and once you take a couple minutes to put that in, I'll tell you guys what the next thing that we're going to be doing with that data in your calculator. All right, so go ahead, take a minute to do so, and we'll proceed forward after that. Everyone's here today, it looks like.
Yeah.
My brother said he didn't like it. 'Cause he didn't remember.
All right, take another minute, and then I'm gonna move on. I still hear some clicking, so hopefully you guys are done. All right, I'm sure you guys text faster than this. Okay, so come on, it's only 10 buttons or keystrokes that you have to look at. Okay? As opposed to 26 letters.
What?
Huh?
We do that every day.
No, I actually like to look.
We're not accustomed to TIE.
Re-enter them.
Oh, you're not? I thought you guys were inseparable from your TI-84s because you guys can't do anything without them.
This is my first year with the TIE. I'm not one of those math girlies.
Imagine doing this class without a without a TI-84.
I don't have it. This is everything for us.
And now you're complaining. Anyways, all right. So hopefully the data's in there. I'm going to again review. Okay, I'm going to review when the data is in our calculator. What do we do with it? How can we use that to look at the conditions? And then I will also go back to this computer output that you see at the screen because on the AP test, for those of you guys who are doing the AP test, you're more likely to see computer output like this as opposed to using your calculator. The reason for that is because on the AP test, they're not going to give you data like this because if thousands of students are taking the AP test, how many of those students do you think is going to input data incorrectly? All right, so it's not likely you're going to input raw data into your calculator, so you do have to see or look at the computer output to get the information. For this example, I gave you the raw data because I want you guys to at least have a feel for checking those conditions, all right? But on the AP test, because they don't give you the raw data, you can't do plots, you can't do summaries, so they typically say assume all conditions are satisfied. But I want you guys at least to see it yesterday and today so that, again, you're not just assuming conditions all the time. All right, because again, who knows if they're right or wrong. All right, so the data should be in your calculator right here. What I'm going to do first is that if I want to plot the residuals, I want to do my linear regression t-test or t-interval. It doesn't matter. So I want to do at least one of those. Doesn't matter, and then just, I don't care about that yet. All right, so I'm just going to press calculate. And then once you do the regression, then the residuals are stored in your calculator. So as a review of yesterday, I'm going to go to stat plot in the top left, second stat plot, and then select the first plot. I'm going to do a scatter plot And let's just put in the raw data first. So in my X list, Y list, I'm going to put in L1 and L2. So this is just a scatter plot of the data. I press graph. I don't see anything. But when I zoom in, I see something. All right, so there's the scatter plot right there. All right, it looks fairly linear. It has that trajectory. I see a couple clusters in the data set. Remember from Unit 2 when we had to describe scatter plots? I see two clusters, the big cluster in the bottom left and the one in the middle. And then the point off to the right, we could consider that as a leverage point, if you guys remember that. Okay, again, you guys should start getting into the mindset of reviewing Unit 1, Unit 2, Unit 3, and stuff too, all right? So that's the scatter plot. It looks, there's nothing on the graph that suggests that it's non-linear, so I'm going to say it's linear so far. To plot the residuals, I had to change my X and Y. So in this case, I'm going to change my Y list to the list of residuals. So to get to your residuals, you have to press second stat to get to the blue, or the list in blue. And then when you have all your lists, you're going to scroll down and then find the list of residuals that was computed doing the linear regression t-test. And then once you have that, you press graph, zoom in on it, and that's the residual plot. Okay? Again, in the residual plot, I don't see any discernible pattern. Like, I don't see a curve necessarily. The variability going left to right on the residual plot is, obviously not impressive, because obviously it seems like in some parts it's closer and other parts it's not as close. So that's not the end of the world, but at the very least we checked it. To check normality, if we go back to stat plot, I want to plot the residuals, make a graphical display. So let's say, for instance, I do a box plot, because box plots will tell me if there's outliers. And I want to do a box plot of the residuals, because patterns in the residuals could inform me of patterns in the data. So if I look at the residuals, that's what we call residual analysis. Then that could give me an idea of what the original data looks like. So graphing that, my box plot looks like that. It doesn't look like there's any outliers. It does look like it could be skewed because there's more variability in the top 50%, more so than the bottom 50%. But it's not heavily skewed. So I think under T procedures, that's acceptable. All right. Let's see. What's another thing that? So those are pretty much the conditions. If you go back to your test menu and you run the regression t-test, item F on your calculator, you have the data there. For this problem, it's a two-tail alternative, so you guys could just select two-tail alternative. We press calculate, and then notice what you're given in the computer or in the calculator output. Notice that you're given the t statistic, so that's our test statistic, 5.03. We're given our p-value, which is very small, 8.7 times 10 to the negative 5. Degrees of freedom is 18, because if we have 20 observations, degrees of freedom is 20 minus 2, which is 18. We have our estimates for the intercept and the slope, A and B. S is the standard deviation of the residuals. And then R squared and R are also there. Okay, so you're given a lot of information from this linear regression t-test. All right. As far as right now, are there any questions about just calculator stuff? No? Okay. All right. So if there's no questions, then I'm gonna go back to the slides and we're gonna start the write-up for this. If you guys still hold on to that that screen with the linear regression t-test, because I want you guys to look at the computer output and see where you can find this information. So notice right here, this part right here, the estimate of the explanatory variable. So weight is considered x, so x and y. So if x is weight, that's my explanatory variable. What is the estimates? I guess this is in the program I use, it's called the estimate. This is actually the estimate of the slope, b. So if you guys look at your calculator at b, you're going to see that this should be the same value. If it's different, then one of us put in the data incorrectly in the calculator. All right? But you should see this in your calculator, 0.41639. That's in your calculator. And then this part right here in the standard error, this is the standard error of b, but this is not in the calculator. Not in the calculator, okay? So just so you're aware that if you needed to find the standard error, you're not going to find it on your calculator directly. So I will show you guys how to find that in just a moment, all right? But I want to go over what else is here, all right? If you guys look at your computer or your calculator, you'll see that A is 68.58443. So this right here is the estimate of A, or the A as an estimate. If you look at the rest of the table, you're going to see that we have a t-value. This t-value for the slope, this is our t-statistic. This is our t-star. If you look at your calculator, this is the same value that we have, that 5.0306 or something. That's in your calculator output. And then this is our p-value right here. The same thing, 8.7 times 10 to the negative 5. This is the p-value. And this is the p-value for a two-tailed test.
Is it always two-tailed or?
Yes, because in the computer, at least the program that I use, it doesn't ask you for the alternative. So by default, it computes the two-tail alternative. But if you wanted the one-tail p-value, okay, all you have to do is take this probability, okay, take this probability and divide it by 2. Because if the two-tail alternative is the left and the right side, right, if you just divide it in half, take one away, you're left with the one-tail. So all you had to do if you wanted to find the p-value for a one-tail test, you just take that p-value in the table and divide it in half. Okay, that gives you the p-value for one tail, whereas if we wanted two tail, we multiply by 2, right? Okay. This other stuff in the table, the standard error in the intercept, the t-value in the intercept, and the p-value in the intercept row, you are not going to use that in this class. All right, so I cross that out. We're only interested in the bottom row or the second row with the explanatory variable, and only the estimate in the first row, okay, which is highlighted in yellow. All right, other things to keep in mind, standard error right here. This standard error, or it says residual standard error. This is S right here. That's also in the calculator. It gives us our degrees of freedom right there. And this is R squared, which from Unit 2, you guys should have seen that before, okay? All right, so there's a lot of information in this computer output that you guys have to know where to find things. And you have to also be able to say, oh, I see, I don't know, for the t-value, I see 5.031. That is not the value of t in your confidence interval. That is not a critical value, that is a test statistic. All right, so be aware that, yeah, the computer will do it for you, but it's useless if you guys don't know what you're using or how to find it, okay? So be very careful when you read the output and just understand what everything means in there, okay? All right. Let's see. I'm going to talk about how to find standard error before I do the write-up for this problem. And then once I'm done with the write-up, then the rest of the time is for you guys. All right. So any questions so far about the computer output before I move on? Hopefully after that Unit 2 test, you guys should know the computer output, because most of you guys got the variables mixed up when it asked you to interpret the slope of what was it, like crop yield and cost or something, if you guys remember that question. All right, so yes, fun times, I know. All right, so I'm going to talk about from the calculator, how can we get the standard error. There are two methods that I could think of, but I tried looking up videos on YouTube on if there's an easier way. I don't think there is, so here we go. So how to find standard error of B. Okay? And you're going to have to use the linear regression t-test for this. Okay? You do not the t-interval. So not the t-int version. You have to use the t-test version. Okay? So the first method to find the standard error, so method 1, is the computer outputs. Okay? Computer output. Because again, right there in the computer output, this is the easiest way. The one that's in pink right there, that's the standard error B. So if you know how to read computer output, you don't have to go soul searching for that standard error B. The second method, in the event that you're not given computer output, then you're going to use the regression t-test. So remember the test statistics. So t star is equal to B over standard error B, right? So by algebra, if you isolate standard error B, it becomes B over t star. Oh, but isn't that just from your calculator, and also that from your calculator or the output? Okay, so if you guys go back to the output right here, or your calculator, B is 0.41639, and the test statistic is 5.031. So just to check, because it's, again, when I was in grad school, all my professors were saying don't rely too much on technology, understand how to also do it manually as well, because again, the calculator functions are good, but that really that doesn't mean you know what's going on. That's basically what I'm trying to say. All right, so in this case, B is 0.4163, I went one over, it's okay, 9, and then divide by that 5.03 something, 31. Okay, so that's from the computer outputs. This is what did I highlight this color as? Sorry, I highlighted that as blue. Okay, so this guy right there, this is the blue thing, and then the test statistic is that 5.03 that you can see in the calculator or from the computer output. If you guys put this in your calculator and just double check to make sure that Mr. Young's not lying to you, all right, because I do that sometimes. All right, then you're gonna see that the standard error is what it's supposed to be over here, which is that 0.08277. Okay, so again, it's important that you guys don't just say, "Oh, a computer will do it for me, so I don't have to know this stuff." All right. Okay, so in any case. That's just one way to check, and that is one way in which you guys can find the standard error from your calculator, because your calculator will give you guys B, it'll give you T star. Your output that I just showed you guys from the slide, I could find the same pieces of information and find the standard error. Okay? So, that's one method. The other method that's a little bit more tedious, well, you will probably think it's more tedious, is that the standard error of B, if you look in the slides from before, that's equal to S divided by S sub S times the square root of n minus 1. So this right here comes from the calculator. So this comes from your linear regression. t-test right there, or it comes from the output. Okay, and then this right here, S sub x, do you guys remember how to find S sub x? One var stats. If you have the data in your calculator, do one var stats, put the x values in that function, you'll get S sub x. All right. Oh no, you can't get this from the output. Okay, so the computer output on that screen doesn't give that to you. So this is actually, I guess this is only for the calculator. All right. So once you have those values, then you could find this. So the standard error, or not, the standard deviation of the residuals is 8.8724. Divide by the standard deviation of the x values. If you guys go ahead and do that, it's going to be 24.5922 or 23 times the square root of n, 20 minus 1. And if you were to put this in your calculator, this is going to be equal to 0.08277, which is the same thing. All right, so there are ways to find the standard error, but your calculator is not going to directly give it to you. Okay, so that is one reason why on the AP test they typically just give you the computer output, because the computer output gives it to you. All right, the calculator will not give it to you. So that's probably another justification on why reading the computer output is going to be very important. Okay. All right, any questions about finding standard error? All right, so in that case, there's no questions, then I'm going to move on to the write-up of this problem, where we're going to see if there is an association between these two variables. All right, so starting the write-up right now, hopefully it won't take much longer, but we're going to let beta, okay, let beta be the true slope of the linear regression model of, in this case, the y is going to be systolic blood pressure, and on the weights, right? And they're both of them, you should include the units in millimeters of mercury, I think, and in pounds, respectively. Okay? To test whether or not there exists a linear association between these variables, an appropriate procedure is a t-test for the slope with the following hypotheses. Null, beta is equal to 1. That's what we're going to typically just work from in all these problems. And then the second one is that beta is not equal to 1. Or sorry, not equal to 0. Sorry. Okay? So those are our hypotheses. We want to find evidence that there is an association, so that just means it can't be 0. All right? So there's that. Step 2 are the conditions. So the first condition is linearity. Going through all those plots at the beginning, those are for the conditions. So the linearity, the scatter plot of the data suggests a moderate positive linear association between blood pressure and weights. Okay? That's all I have to say. I checked the scatter plot, it looked linear to me, so here we go. The next one is independence. So because the sample of 20 men were randomly selected and randomly selected without replacements, independence can still be achieved because the population of males between the ages of 25 and 30 is much larger than 10 times n, which is just, if I have 20 male subjects, times 10 is just 200, right? And I'm pretty confident that there are more than 200 males out there between these ages. Okay, that's independence. The same condition that we had before. All right, the next one is normality. This one was a little bit it wasn't cleared convincingly, but again, we're gonna have to be very loose with our expectations for the data. So a box plot of the residuals suggests no extreme skew and no extreme outliers in the data. Therefore, a t-distribution with 18 degrees of freedom is a good approximation for the sampling distribution of the sample slope B. Oops, question mark. All right, and again, typically if you guys refer to graphical displays, you do have to draw them, although again, I'm not sure exactly just how strict they are on this, but again, just to show you guys, remind you guys what the box plot kind of looked like that, okay? And then the scatter plot, there was a cluster down there, there was some cluster right there, and there was a leverage point there. Okay, so you should sketch out all the graphical displays that you refer to. Okay. The next condition, I know there's a lot, equal variance. So a residual plot of the data suggests a roughly uniform variability among the residuals across all x values. Therefore, this condition is satisfied. So I don't even think we have to say anything more. Okay, so that's that. And then the last one is SRS. Do we have a random sample? It said it did. So it stated that the 20 males in the study were randomly selected. Okay, in first block, because someone mentioned that there's a lot of conditions, do we have to remember them all? The answer is yes, you do. A good way to memorize them is if you look at the conditions, how I ordered them, you'll see that they'll spell out an acronym LINES, okay? Linear, independence, normality, equal variance, and SRS. So that's an easy way to try to remember those conditions, okay? All right, and then the conditions are done. And then now we go to the calculation, and I'm gonna try to, again, refer back to the computer output for this. So step 3, my test statistic T star with 18 degrees of freedom is equal to B over standard error of B, which is equal to, and if you look at the computer output, it's right there. That's the estimate for B, and then the standard error is right here. So if you look at the computer output, I'm getting this value from there, and this value from there. All right, And this test statistic is equal to 5.031. That is also given to us in the computer output right here. So when it says t-value, this is the t statistic right there. And the p-value that's associated with this t statistic is given to us right there. So that test statistic over there, when I divide this with that gives me that. And then the p-value for this is that. Okay, so again, understanding what these values are and how to use them is important. Okay, all right, and then it also tells us the p-value. So the p-value in this case is 0.0000869, which everyone in this room should say that yes, it's clearly less than alpha. So therefore, our interpretation is as such. Okay. Okay, so because the p-value of 0.000869 is less than the 1% level of significance, there is convincing statistical evidence that there exists a linear relationship between systolic blood pressure and weight among males between the ages of 25 and 30. All right, and there it is, right there. Okay, so that's the write-up. Again, it looks like a lot because of those conditions, but in a problem where they're only going to give you computer output and no data, and they say assume all the conditions are satisfied, that step 2 just goes away. So you can see that if you don't have to do the conditions, which is probably a safe bet on the AP test, then the rest of the work is actually pretty straightforward, especially if you know how to interpret that computer output. Okay? All right, so with that, that's the end of the example. Do you guys have any questions? I believe on your homework you have 2 problems where I'm going to ask you guys to check the conditions. So like this, the other 2 problems, I say the conditions are already assumed to be true or checked. Okay, so you have 2 that are checked, 2 that are not checked. Okay, so again, that's just the one homework assignment for this whole unit, so that's why I wasn't afraid to give you 4 problems for this one. All right, so any questions? Because if not, then I think I'm done. Unless you guys want to see another example. Yes. A Band-Aid? I do have a Band-Aid. Do you need it right now?
I can wait.
Okay. I think I'm almost done. I think. It seems like everyone in this class has had their fair share of stat lectures. All right? But if there's no more questions, then the rest of the time, the 25 minutes or so, is for you guys to do your homework. And again, do not procrastinate on this homework assignment. It's due tomorrow. But if you're going to work on it tomorrow in class, you're eating up review time that I'm giving you in class. So again, I would much rather you guys use class time to get questions answered as opposed to working on work that you should have already done before class. All right, so I will post the homework right now. And let's see, you guys are 3rd block. And I advise you guys get started right now. There are 4 problems, so please get started on those. Tomorrow I will tell you guys more details about what your final is going to look like. I might have some released AP tests that I could share with you guys, and then the rest of the time I don't have anything planned for the next 3 classes. So